Okay, let's do this thing. Wait, what? What just happened? That's not right. Okay. So, all right, let's go quickly through what all this is about. All right, so what is this book about? From sections 1.1 to 1.7, we have basically the general idea of modeling, and then they introduce basically the simplest model that includes all three quantities that comprise models. Parameters that are constant and don't change. They're fixed for a given differential equation. The independent variable, which is time, and the dependent variable, which is basically what we have with respect to the change. Or I mean, what is changing. Um, okay, so it's first order because it only contains first derivative. ODE, this whole book is about ODEs, so we're not even going to talk about PDEs. All right, an equilibrium solution is basically some zero. So if the population starts off at zero, it's going to stay zero forever because the derivative, the change, is zero. So in the equilibrium solution, the main thing is an equilibrium. So there's IVs, DVs, and Ps. Okay, so that's like what makes up a model. Now, order of a model is defined as the highest degree dir. Okay. Now, what else did we go through? Example, d2x dt squared equal to x is second order. Okay. So now we are going to go over the definition of an equilibrium solution. Okay, an equilibrium solution is written, let's see, this. P of t is equal to 0 is, and also P of t equals 50. Both examples. Okay, so anyways, this is the form that the teacher's going to want equilibrium solutions to be written in. Init condition is P of t0 for some t0. It doesn't really matter. It doesn't have to be at 0. It just frequently is because a lot of the time we're talking about autonomous differential equations, which don't depend on t. So it doesn't really matter. Okay, an IVP is basically just a DE plus a IV. You just get an extra piece of data about, that constrains the solution trajectory, because there's an infinite number of trajectories, and if you have one point, then you know the rest of it for the most part. That comes up in 1.5 existence and uniqueness, but if the functions all chill. Okay, a solution okay, so IVP solution is a function p of t such that okay. So that's the definition of an IVP solution. So IVP, you just have a basic differential equation, and then you have some value at some point in time. Then a solution is basically one that satisfies this differential equation for all time, and also matches the initial condition. Whoa. Did the bee just show in the shot? I wonder. That's funny. Okay, so all right, so they basically guess. Okay, so here we go. This is important. So particular solution to IVP is one of the P of T's. General solution is a family of functions like P of T equal to CE to the KT. Okay, then they introduce another model with carrying capacity, and it has a special name. Logistic x dot equals x times 1 minus x. Okay, then they analyze that. They find that there's two equilibrium solutions. Has two equilibrium solutions. And then it has this shape. Okay. Predator prey. What do they show in predator prey? They just talk about. Yeah, okay, and I see why they're introducing that, because basically, one, there can be interaction between variables, and differential equations are not limited to single variable. They can be as high to, so okay, here we go. Okay, so yep, composition basically, making, okay, so the three methods of studying DEs: qual, quant, or analytic, I guess, analytic, and numerical. All right, so we're not going to actually do these exercises. Okay, analytic. So this is 1.1. Now we have 1.2. Analytic. Okay. As a function of the IV, when substituted in the equation. Okay, so this is worth solution checking. Say y dot equals y. We can check y of t equal to 3e to the t is a solution by computing d 3e to the t dt and set that equal to 3e to the t. Okay. Checking a given function. Okay, then they do another example. Example 2 is, let's say we have y dot is equal to y squared minus 1 over t squared plus 2t, and someone gives us a candidate y1 of t is equal to 1 plus t. So we take the derivative of that, so y prime is equal to just 1. Okay? So then we have on the left-hand side, we have 1 is equal to, and then we have y squared, which is 1 plus t squared minus 1 over t squared plus 2t. And so here we get 1 plus 2t plus t squared minus 1. This cancels. 2t plus t squared. This cancels to 1. So we get 1 equals 1. So there we go. We verified it. Okay. Now we can go on. IVPs and general solutions. Okay, they do integration. Okay, they again introduce general solution in a little bit more detail. Okay, here we go. Separable DE. Defined as y dot equals f of y times g of t. So they're separable. Doesn't really matter what they're called, but that's the general idea. And it turns out that those we can find. Those we can easily find solutions for. And then autonomous DE is y dot equals f of y. Recall general form is y dot equals f of t and y. Okay, so how to solve them? You got to get them on the corresponding sides, right? Yeah, like that. Okay. Okay, and then we find an explicit solution. What's really going on? Okay, so this goes into the formalism of like why we're allowed to do what we think. It's possible to separate variables into DE. Yeah, this is a good case. Y dot equals y squared is weird because solution is y of t is equal to 1 minus 1 over t plus c, which lacks a which general lacks y of t equals 0, which also exists. Okay, so there we go. Okay, implicit solutions are fine if we can't do better, which basically means, like, example, ln of absolute value of y plus y squared over 2 is equal to t plus c. We might not be able to find a there's another problem that arises, is often impossible to perform the integrations. Okay, and then they introduce basically, look, this is not going to work for all of our stuff because sometimes it's just going to get way too annoying. Okay, then they motivate it with a real world example. This one, I remember I had a little bit of a hard time remembering. But I think it's going to be fine. Okay, now it's just a bunch of motivating problems. Mixing in a vat. Okay, it's more integration. Okay, great. Okay. This is going exactly kind of how I wanted it to go. It's like a relatively fast notes section, and then we just do a bunch of problems. Okay, so slope fields. So what I'm looking for here is maybe like syntax, or like, because the thing is, what you don't want when you're doing math at this level is for a teacher to dock you for silly syntactic things because they don't know that you know better. So you can't really do any abusive syntax. So the idea here is you basically sample the space, you compute f of ty. Okay, so you take y dot equals f of ty, compute f on the grid, draw small lines. Okay, and that sort of gives you an idea of the behavior of the solutions. Oh yeah, okay, so this is a very important picture that I'm going to draw in my notes. Okay, special cases. So this is going to be y dot equals f of t. If it only depends on t, then if f only depends on t, then if t1, y1, t2, y2, the f of these points are equal as long as t1 equals t2. That amounts to, we have this line, all of the slopes along that vertical line will be equal. Similarly, we have y dot equals f of y, and here we're going to have a okay. So that's actually important. So here, for an autonomous, we have horizontal lines have equal slopes. For just depending on t, there. I mean, honestly, it doesn't even really matter because it turns out that you can just convert non-autonomous differential equations to autonomous differential equations by introducing a new variable. So it's like not as big of a, but anyways, they're trying to ease you into this. Okay, here's the motivation behind why qualitative actually has value. We could have found an explicit, but they're basically saying it's too much work, but with a little bit of work, you can figure out the general form of the solution. So yeah, so here's like this here's a really complicated one that you're like, hell no, I'm not integrating that. But then it turns out we can just recognize some stuff about the zeros and all this. This is all introducing the bifurcations, which is like the ultimate way of doing this. Okay. I hope there's not going to be too much on this capacitors and all this stuff. But it's fine. Okay, Euler's method. Euler's method. (1.4) Euler's. The main thing here is, I mean, it's just so basic. I just want to write down the formula pretty much. It's going to be x k plus 1 is equal to xk plus delta t times f of tk xk. That's the formula. Let's go find it. And then they actually show the derivation. They say, look, we have this tangent line. This is like, it's a super simple derivation. I just don't feel the need to do it. But that's Euler's method. And pretty much higher order, I don't know if they call it order, but, whatever. So, okay. Okay, and then they show, here's solving a bunch of things, whatever. And then how it converges. And then and then it shows, look, things can go wrong when slopes get really big. And I think they show an example. It's like, look, if it goes negative, you know something's wrong because this is a non-negative. Well, not this one, but there was another one where it basically says, look, you can use qualitative methods to validate the numerical methods. Okay, so this is like the bird's eye view of the whole class, I guess. Okay, so I really didn't write very much. I only wrote the definition of the method. Okay, 1.5, what is this one? This is, oh yeah, this is an important section. And I expect to spend a good amount of time doing this one. I'm going to get some more water, though. All right. I'll write that down. So we have 2x fifth minus 10x plus 5 equals 0. We easily find f of 1 equal minus 3 and f of minus 1 equal to 13. We can use this as proof that there exists a solution, to f of x equal to 0. Okay. Damn it, I'm getting that 4 p.m. freaking sleepy attack. I'm getting sleepy attacked over here. Okay. But we did not show that that's the only solution. And we didn't really approximate it. So we can discuss the existing solution without having to compute them. Great. Okay. Okay, what is the point of the extendability? All right, so let's just write this down. Existence theorem. F of t, y continuous in the set of ty's such that a is less than t is less than b and c is less than y is less than d. Okay, if it's continuous in that rectangle and t0 y0 is a point in, let's call it s is equal in, then we know then there exists an epsilon greater than 0 and a function y of t defined on t0 minus epsilon, t0 plus epsilon, that is a solution to the IVP. The solution has a very small domain of definition. The theorem says there exists an epsilon greater than 0. So it could be really, really small. It's actually crazy to me that this blows up to infinity in finite time. I wish I had time to. I mean, it's just crazy that actually can happen. This book is Blanchard. Differential Equations Blanchard. But right now is review because I got a test. Um, there's a danger the solutions blow up as t increases. By looking at the solutions sketched by the slope field, we can't really tell if solutions blow up in finite time or if they stay finite for all time. So we try analytic methods. This is autonomous, so we can separate and integrate. That's all good. Anyways, we get arctan, we get y of t is equal to tan t plus c. It's actually crazy that they blow up. But yeah, it definitely does. Why do I think it's crazy? I think it's crazy because y dot equals y squared. Yeah, it's growing fast. But it just doesn't seem like it would grow fast enough to reach infinity in finite time. I don't know. That's really weird to me. But I don't think it's going to be part of the text of the test. Okay, the next part that's important is the uniqueness theorem. So this theorem requires, in addition, I'm praying there's no absolute values on the test, dude. I hate absolute values. All right, knowing that the solution to an IVP is unique is very valuable. If solutions weren't unique, we'd have to worry about all possible. Yeah, so okay, wait. The value of having this is if solutions not unique. If solutions then we would have to worry about all possible solutions. That made more sense earlier, but I don't really get it. Different solutions can give different predictions of how the system will work. There's a very good theorem. Okay, so the theorem. If f, t, y, and partial of f, partial y are continuous, in S, okay. And we have a t0, y0 in S, and for the IVP, we have two solutions. then y1 of t is equal to y2. Okay, great. So yeah, and you can use this to actually say some pretty powerful stuff about differential equations, at least on the definition of that rectangle. The thing is, it doesn't tell you. What I don't understand about uniqueness and existence theorems. If we have a DE that's DEF of TY continuous everywhere, and del F del Y also, this still only gives us that there exists an epsilon greater than 0 such that the solutions are unique. Right? We don't actually know. Does the theorem let us say that we have unique solutions everywhere? Once you know that there's a solution, right. Yeah, you patch it. That's cool. Okay. They don't actually get into that, but yeah, you could just repeat it. Yeah, that's so cool that you could patch it together. I never actually thought about that. Wait, what? So wait, hold on. Let's read it. Two different solutions through 0, 0. You have the trivial solution, which is the steady state, the fixed point, the equilibrium, whatever you want to call it. The non-trivial solution is this whole thing is weird because I forgot about the patching them together. Okay, but anyway, so this is at any time you just hop off and you go to the next. Okay. So here's their example where uniqueness fails. Okay. Okay, applications of the theorem. This is good. If two sols in the same place at same time, then they are the same function. That's the important thing. All right, the role of the equilibrium. Consider this really complicated expression. Finding it is really hard. Even though it's autonomous, you could probably try to do it. I'm not going to try that. On the other hand, if y equals 2, the right-hand side vanishes. Thus, the constant function is an equilibrium solution. Suppose y2 satisfies this. The uniqueness theorem implies that, right, this is sort of a contradictory thing, that y of 2 is less than, y2 of t is less than 2 for all t, because it can't touch y of 2, because otherwise they'd be in the same place at the same time, which would they be the same, but they're not the same, so they never touch. That's what that's about. Okay, so this is all just wait, let's look at the bifurcation analysis of y minus 2, y plus 1. Well, there's no parameters, so you can't do a bifurcation plot, but what you can do is if you have y of t on the y-axis and y on the x-axis, which is a hilarious thing to say. Okay. All right, I get it. Numerical approximation. Okay, here's the fun thing. We know that it like is less than 0. Okay, great. So this, which problem was really good? This problem was really good. 17. Okay, this is the one that I want to actually practice kind of the most because I just did so poorly on trying to calculate those integrals a few days ago. I just got freaking cooked by the integrals in the. Let me see if I can remember these problems. This is a long section too. I mean, I generally understand phase lines and bifurcations pretty well, but it's the integrals that I'm scared about. We probably will have to sketch a phase line. I hope I'm allowed access to Julia or Python because otherwise it's gonna be really annoying. All right, it's 420. Bro. All right, wait, let's just go through this section. It'll only take a little bit. All right, so what's in here? I'm not even gonna write notes. Okay, so this builds on what we saw earlier, which is that if you have an autonomous differential equation, it doesn't depend on t, it only depends on y. That means that you can translate the solutions left and right, and it's going to be identical pretty much. Okay, so here's the slope field for an autonomous differential equation, and you can see, that for any line, horizontal line, the slopes are all equal. So because of that, you can just draw one line. Okay, this rope metaphor was so dumb. Okay, so yes, the way that you construct a phase line is you first just draw dots on the equilibrium points. Then you can either do linearization or you can evaluate the derivative. And I like the geometric understanding of why linearization tells you whether or not it's a sink or a source. Um, okay, so how to do it. Here's a little algorithm. How to use them to sketch solutions. You basically just extend it out and then you just draw lines, baby. Wait, 3 equilibrium points. Where's the third? I guess it's, oh, it's that. Okay. All right, I wanted to read this. This one's good. Warning, not all solutions exist for all time. It's always these quadratics, bro, with this tan H nonsense or something. I hate those. These finite time blowups bother the hell out of me, man. The solutions just end. It's so weird. I don't like these nasty functions. I don't like them. They're nasty. Okay, here's the classification stuff. Sync, source, node, that's all easy. And then I think... Okay, here we go. Linearization. You take f prime. So the whole idea is that if you draw a tangent line at the equilibrium point, you can see that... Okay. Forget linearization. Here's what we're going to say. Right here, this is clearly a sink. And the reason for that is the slope for y less than y0 is positive. So it's going to approach y0. Similarly, for y greater than y0, the slope or the slope is negative, so it's decreasing. Dy dt is negative here. So it's going to decrease down and approach y0. So now if we drew a tangent line, the sign of this is going to tell us whether we are going to approach it or we're going to go away from it. So that's what linearization tells us. And then the reason why f prime equal to 0 tells us nothing is simply because if we look at the graphs of x squared, x cubed, they're both going to give 0 for f prime, but one is a node and the other one is a this is a source. Okay, so that's what linearization is all about. Okay. Okay, great. So we just finished 1.6. Okay, so the problem here that I got cooked by is just integrating, I think. Is that true or was it? I think it was 1.5 actually. Okay, let's just get to the review exercises. I'm going to take a 5-minute break and then we'll get to it. Let's see what's in here. Oh, true false stuff. True false is great. True false questions are really powerful. We'll do those. All right. Okay, basically these definition of vocab. So we're skipping 2 sections, but that's okay. If it seems like something that we see, if we see linear in here, we can attempt it, but know that maybe we don't have the tools to do it. Okay, I'll be right back. All right. Let's just hammer out these problems, man. Okay, 1. So these are going to be the review, chapter 1 review. All right, problem 1. Give an example of a first-order differential equation that has the function y of t equals 2t plus 3 as a solution. So basically what we're looking for is damn, wait, this one's hard. What the hell? Give an example of a first-order differential equation that has the function y of t equals 2t plus 3 as a solution. I'm pretty sure it's just going to be f of ty is equal to 2. dy dt equals to 2. I think that's it. I think it's just dy dt equals 2. You take the derivative, and then that's it. Yeah. Okay. I'm not crazy. Why was that so tricky? Kind of tripped me up for a second. All right. What is the general solution of the differential equation? Okay, here we go. I want to do a couple of use substitution if possible, because I feel like he cares about analytic solutions. So y dot equals 3y. So what we want to do is dy dt is equal to 3y. We divide by 3y, we get dy over 3y is equal to dt. Integrate both sides. We can pull out the 3, leave it over there. So we're going to get ln, absolute value of y, is equal to 3t plus c. Now we call the exponential on both sides, and we get absolute value of y is equal to e to the 3t plus c. But then that's going to be equal to e to the 3t times e to the c, which is and then we just let c equal e to the c. But actually, the thing about that one is, but since we have the absolute value, oh yeah, we probably will have an absolute value on the test because this shows up all the time. So absolute value of y is equal to, let's just say c e to the 3t. Now, I really don't like the absolute values. I don't know why they trip me up so much. Okay. Okay, so then this becomes y is equal to plus or minus a e to the 3t. So basically, you can just get rid of it in that case. Okay, problem 3. Find all equilibrium solutions for, okay, so y of t, wait, find the equilibrium solutions for something that only depends on t. Okay, look. Let's just say this. dy dt is equal to 0 if t is equal to 0 or um that's it. That's it. So the equilibrium solutions is going to be y of t is equal to 0. No, I don't know how to specify this because how do you specify this solution? Right, for all t. So it just doesn't exist. So they're trying to trip you up. There are no equilibrium solutions because y of t must be constant for all but yeah, that certainly can't be the case. Okay. Find one solution of the differential equation. So what they want us to do is just 0. Y of t sine no, equal to 1. It's going to be 1. Oh, what? Silly me. So this is just going to be y of t is equal to 1. Or wait, no, pi over 2. Wait. Oh, sorry. No, wait, hold on. Wait. Oh, no. What am I talking about? I don't know the definition of sine. Sine of 0 is equal to 0. So y of t equal to 0 is the solution. There we go. Boy, oh boy. Find all the equilibrium solutions of this differential equation. I think it's just y of t is equal to minus 1. I think that's the only one. They made it look complicated, but really, there's only one. Oh, but the thing is, wait, hold on. Before I do that, yeah, no, I stand by that. Cool, we got it right. All right, number 6, sketch a phase line. Okay, so the fixed points are going to be k pi. So 0 pi, 2 pi, minus 2 pi, etc. So what we're going to do is we're going to draw a phase line. 0 pi minus pi. Now, I don't really want to take the derivative, but maybe we should. Okay, actually, we'll just do this. Pi over 2, sine pi over 2 is 1. Right? What the fuck? Okay, that's what I thought. So, actually, is sine listable? Probably is. Yeah, of course it's listable. Okay, so that means that that for minus pi over 2, the derivative is y dot is wait. No, it's flipped because f. Oh, really? Wait, can we plot this? This notation's so stupid. Is this the same as sine of x? It's the same plot. I hate this notation. This notation always confused me, bro. Because it's not an iterated map. I don't know. It's not like or a nested function. Anyways, so here we have a bunch of they're all pointing up. They're all pointing up. They're all pointing up. It's all pointing up. Okay. That's it. So the phase line just goes up and up and up. So they're all node, node, node. Okay, great. Banging this out. Given a autonomous, separable, linear, and homogeneous. What is homogeneous? I don't think we know this yet. Okay, great. So the first usage of the word homogeneous is in section 1.8. So we're good. All right. So we're going to skip 8. Suppose the phase line to the right is the phase line for the autonomous differential equation. What can you say about the graph? Um, it's just going to be like a parabola, right? It's going to be wait, no. It's going to be like a cubic or something. It's going to be like y cubed, except it's a source. So it's going to be like minus y cubed. So it's going to be like minus y cubed, source, and nothing else. Let's see how well this does. But it's going to be, I'm almost positive that's an adequate solution. Just to say that it's a source, and it's like y cubed, minus y cubed. How many are there? Well, there's a lot on the linear. $42 is pretty weird. It looks like we have. $49 is probably pretty good. Okay, we need practice integrating, so I'll do some of these. OBS disconnected. Okay, we're back. Okay, I wanted to do 10. 10 looks cool. Um, it's got to be a. Well, actually, you know what? This might be a trick question. I think it's just a equals -4. I think it's the obvious thing. It's like you go. Yeah, for a greater than -4, solutions increase and then they decrease. Okay, let's do some true false. Hell yeah, I love true false. Okay, 11. Y of t equal to minus e to the minus t. Solution to. Okay, so. Yeah, okay, good. So we're going to get. Yep, I think that's true. All right, so this is true. E to the t equals me. Okay, yeah. So, all right, we'll do them all and then we'll check our answers. But I'm almost positive that one's right. All right, the separable, every separable. No, what? That's false. That's stupid. Okay, 13 is true though. If we have. Yeah, no, it's just true. 14. Every linear. We're going to skip that one. Skip. 15. Every separable differential equation is homogeneous. Skip. 16. Oh my gosh, there's a lot of this linear stuff. The solution of this. to 0, sine of 0 is 0, so that becomes 0. This becomes 1. So we have 2. So we have 1 times 2, so it's positive. And now I really don't like non-autonomous differential equations because I never know what to think about the t. What do you do with the t? Wait, let's copy the... This could be negative. This could be negative. This could be negative. But but you know what? Because of this plus 1, this thing has to be, this thing at a minimum is 0, I believe. Because I think if we did, well, I don't think this is exactly right, but if sine x plus cos x, I think we get, oh no, it's not. Okay, so maybe I'm wrong. Notice that right. Oh, right. Even if the derivative goes negative, you're never going to cross it because you started above it. Okay, so this is going to be true because you started above. And I mean, it's worth checking that this thing is continuous and its derivative with respect to y is continuous, but I think it is. Above y equal to 3, and it's continuous, and partial f partial y is, and y equal 3 equilibrium solution. Okay, so that's true. Yeah, that's a good problem. Suppose that f of y is a continuous function for all y. I don't think that's true. Wait, is it true? No, that's not true. Think about y cubed. That's false. Consider x dot equals x cubed. That's definitely false. Damn, it's already 5, bro. Yeah, exactly. Suppose continuous differential for all y exactly one solution. Wait, that doesn't even make sense. I think this is like obviously false. There should be an infinite number of them, right? Well, actually, hold on. What? Yeah. Because all you're given is that f of y is continuously differentiable. I really don't like these non-autonomous. They're so stupid. Okay. T is equal to 0. This equals 1, right? The initial condition is negative. I'm pretty sure if y0 is less than wait. But dude, I don't know. This one's weird. I think that it's gonna read it wrong. How did they integrate that thing? Okay, I think the integrating factors. Yeah, okay. Yeah, so that's why that one was so hard for me, because we haven't even covered it yet. Okay. All right, so 21 is autonomous and separable. Autonomous, therefore, implies separable. Okay, and let's find its general solution. So dy over 3 minus 2y is equal to dt. We integrate. See, this is where I need the practice. So how do I integrate this? So, okay, so is equal to du over u. So we're going to get minus 1/2 ln u is equal to t plus c. So then we back substitute, we get minus 1/2 ln absolute value 3 minus 2y is equal to t plus c. We multiply by minus 2, we get ln 3 minus 2y is equal to minus 2t plus c. C just absorbs the thing. Then we exp, and we get 3 minus 2y is absolute value is equal to e to the minus 2t plus times e to the c. So then we have 3 minus 2y is equal to plus or minus c e to the minus 2t. Okay, then we have it's going to be c e to the minus 2t minus plus 3/2. Please tell me I have this right. C e to the minus 2t plus 3/2. Let's go! And I didn't even have to do this linear hack. I just used u sub like a man. Let's go. Okay, so here, I do know how to do these ones, because this one's clearly separable. It's separable, non-auto. And then we're going to ignore all the homogeneous and linear and all that stuff, because we don't... Because I don't even know those definitions. So in this case, so we know it's separable because f of t equals t and f and g of y equals y. Okay, so we're going to do dy over y is equal to t dt. So we're going to get ln of y is equal to t squared over 2 plus c. So then we get y is equal to e to the t squared over 2 plus CE to the whatever. Okay, so I got CE to the t squared over 2. Okay, great. So we at least have the easy examples down. I'm pretty sure this one is not separable, so we have to use the other technique. Yeah, exactly. The first thing is, hey, look, recognize it's linear. Now this one is good. I want to do this one. So we have f of t is equal to t over 1 plus t squared. G of y is equal to y. Dy dt is equal to, okay, so we're going to get dy over y is equal to t 1 plus t squared dt. Shit, I don't know how to integrate. We're going to get ln y. Oh, you know what we do? Okay. Let u equal 1 plus t squared. Du is over dt is equal to 2t. So then dt is equal to du over 2t. So then we're going to get, so the integral is going to be ln of absolute of y is equal to, it's going to be the integral, it's going to be t, it's going to be du over 2t times t over u. I think. Yeah, because we substituted dt. All right, great. So we can cancel the t, and then we get 1/2 integral du over u, which is going to be 1/2 ln u, abs of u. And then we're going to get, so let's just get over here. So we're going to get ln abs of y is equal to 1/2 ln abs of t over, oh, no, hold on. It's just going to be ln of 1 plus t squared plus c. We can exp, and we get, how do we do this? What? Hold on. If I do the exp, I get y is equal to, No, wait, what am I talking about? It's going to be e to the 1/2 ln 1 plus t squared e to the 1/2. So you keep an eye on the time, dude. Oh, yeah, dude. Because 1/2 ln x is equal to ln x to the 1/2. That is what I was missing. So then this becomes y equals c 1 plus t squared to the 1/2. So okay, cool. All right, so I just missed an identity. But honestly, okay, that wasn't the worst. Okay, that was 24. 25. It doesn't look separable, so I'm just going to ask its solution. It's going to say recognize it's linear. Recognize it's linear. I guarantee it. What's going on? Here we go. There we go. Now this one I don't know about. I'm pretty sure that this one is a trick one because it actually is separable, but okay, because actually I'm not so convinced. If you multiply t by 1 and try to absorb it, it doesn't really do what you expect it to. Yeah. I mean, that's psychotic. Okay, let's do that one. 26 we skip, 25 we skip, 27. dy dt is equal to 3 plus y squared. All right, so this one, I don't know how to do that one. I think that one also might be some weird homogeneous linear or something. No, I feel like we must be able to do that one. Why can't I do that? Ugh, fucking rule. Shit, I'm not gonna memorize all the. Okay, I really hope that something like that does not show up on the test. That would suck. I'm totally not gonna memorize that. Okay, this one maybe I'll be able to do. Um, and I feel like something like this is gonna show up, dude. Come on. Maybe it's maybe it's the same thing. Mm, 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 mm. Mm, 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 mm. Okay, so this is partial fractions. Oh crap. I just don't remember them. I don't remember how to do them. I don't think I'm gonna learn in the next hour. So let's just hope that nothing with a trig integration or partial fractions or any of the obscure rules. I can do the basic U sub. The formula is okay. Let's just hope that doesn't come up because I'm pretty shaky on that. What other rules are there? Okay. Well, it's probably good I did that. A little bit of that. This one, integration by, what was this, partial fractions? Can I look at how they did that? How did they do that? Okay, partial fractions. We have dy over y2 minus y is equal to dt. So we notice that 1 over y2 minus y is equal to 1/2. Wait. 1/2 divided by y plus 1/2 divided by 2 minus y. The way this works is you like multiply out like y over y. You gotta recognize. You gotta recognize, dude. All right, that one looks like a linear thing. This one is integration by partial fractions. Let's see, is there an easier way to do that? Because, yeah, we should probably... It's not a bad idea considering how much the logistic equation comes in handy. Once you spot, you recognize as the logistic equation with growth rate R equal to 2 and carrying capacity K equal to 2. You can then immediately write down the known general solution. Okay, so maybe that's what we need to do. The logistic equation general solution is y of t is equal to, for this is going to be dy dt is equal to ry times 1 minus y over k. So it's going to be k over 1 plus ce to the minus rt. Yeah, maybe we memorize that one. Oh boy. I'm going to go back to this one. Let's just see. What problems are in the section? Bro, I'm stressed out. Okay. Okay, maybe we should just pound these. I'm gonna pound them. All right, instead of doing this, let's just pound them. Let's just pound them. Let's go. Okay, so number 5, we have t squared y squared. So that means we have dy over y squared is equal to t squared dt. So that means that we're gonna get so this is actually y to the minus 2 is equal to t squared dt dy. Okay, so then what we're going to get is minus 1 divided by y is equal to t cubed over 3 plus c. So then we multiply by y, and so we get minus 1 is equal to y times t cubed over 3 plus c. Then we divide, then we get y is equal to minus 1 over t cubed over 3 plus c. Okay, so let's just I just feel like integration is my weakest part. I feel like I understand bifurcations and I understand phase lines and Euler's method and okay, I got that one right. 6 ln y is equal to t5 over 5 plus c. We're gonna get absolute value of y is equal to c e to the t5 over 5, and then we're gonna get so that's that. So let's do this one. Great. So what we need to write though is y of t is equal to c e to the t5 over 5 for c in the reals. That's like the true way to write the solution. The general solution. Number 7, 2y plus 1. I don't like these, man. But actually, because it's okay, that one's actually easy. I can do that one. 2y plus 1 is equal to dt. So if we let u equal 2y plus 1, then du dy is equal to 2. So that means that dy is equal to du over 2. So that means that we're going to get 1/2 integral u over, or du over u is equal to t plus c. And so then we're going to get 1/2 ln 2y plus 1 is equal to, so then we're going to just get 2t plus c. So then we're going to exponential, and we're going to get 2y plus 1 absolute value is equal to e. We're going to get c e to the 2t. So then we're going to get 2y. So we're going to get y is equal to c e to the 2t minus 1 half. Y of t for c and r. Okay, let's try it. I'm pretty sure I got it right, though. All right. Get the juices flowing, bro. It's nothing like stress to make you really work harder. You know, this time yesterday I was like, I'm sleepy, bro. I'm wide awake. Oh, God, I'm wide awake, bro. Oh, God, I'm wide awake. All right. Perfect. That's exactly what I wrote. So I'm happy with that. But we should get to some of the harder ones. See, like this one, if I get something like this, like I know it's gonna be like something arctan, but I just don't know the rule. dy over 2 minus y is equal to dt. So what we're gonna have to do here is gonna be like a -1 integral. It's just gonna be like a -1 ln 2 minus y. And then it's gonna be like a t plus c. So then we're gonna get ln. So then we're gonna get like minus. So then we're gonna get like e to the minus t, and c is still ce to the minus t is equal to 2 minus y. So then we should get y is equal to ce to the minus t plus 2. Oh God, I'm wide awake. Perfect. Perfect. I got it right. Okay. We got to keep going though. Yep. E. Okay. Come on, come on, come on. Okay, number 9. We have e to the y dy is equal to dt. So we integrate the integral of ey. It's going to just be e to the y is equal to t plus c. Then we do ln. So then we get y is equal to y of t is equal to ln t plus c. Now I feel like there's some details in there that I never mind. Oh yeah, what were those problems actually in here? It was the these ones. This is I didn't understand at all. Why doesn't this contradict the uniqueness theorem? Bro, I feel like I'm capping out. I feel like I can't. Maybe I should just take a break for the 30 minutes before the test. Is that like chickening out? All right, let's just do a couple more of the like hard ones here. Like this one, 1 plus x squared. I know that it's going to be like, so we have dy dt or dx. Dx dt is equal to 1 plus x squared. So in this case, the rule is that arctan of x is going to be equal to t plus c. So then x is equal to tan t plus c. Is that right? Nice. Okay, good. So at least I kind of memorized it. it's just funny, like, what they make you memorize. Like, I don't know, man. Memorizing math, it just something about memorizing math that's like, what? I don't know. If it's like structural, I don't know. Maybe you could argue that from a certain point of view, that's pretty structural. But in my mind, it's just memorizing a rule. I don't know. Who knows where it's gonna go? Okay, so this one's interesting because okay, so dy dt is equal to what? 2ty squared plus 3y squared. So what we're going to do is factor it. We're going to get y squared 2t plus 3. So then we're going to get dy over y squared is equal to 2t plus 3 dt. And then we're going to get minus 1 over y is equal to t squared plus 3t. So then we get y of t is equal to minus 1 over t squared plus 3t. Oh, plus c. Plus c. We're spamming integrals today, man. It's probably going to do a partial fractions thing, but... Oh, no. Okay, so it separated them. Nice. Minus t squared plus 3t. Okay, cool. I'm feeling good. I'm feeling good because these are working for me. Y dy is equal to t dt. We're going to get y squared over 2 is equal to t squared over 2 plus c. Multiplied by 2, we're going to get y squared is equal to t squared plus c. Then we square root, we're going to get y of t is equal to the square root of t squared plus c. Okay, I'm getting pretty fast at these. Hopefully this is gonna actually count for something. Oh, we need to do a plus minus that I forgot. Not that one. No, this one we can do. This one's easy. This one's pretty easy. This one's hard. How do you do that one? Well, actually, no. How do you do this one? I don't know partial fractions. Okay, but that is how you do it. Okay. Okay. You just need to be able to recognize. Like this one. This one. Okay, wait, hold on. So, okay. This one I can definitely do. You multiply both sides and then you integrate in parts, and that should work out. You could also just do a power thing. I forget how that works, but this one is going to be the same as this one, just with some extra work on the on the right hand side. This is the partial fractions one that I didn't really know how to do. Let's do 18. 18 looks pretty good really quickly. 1 plus 3y squared dy is equal to 4t dt. So we integrate wait, I just want to see how it's going to do this thing. Because I think it's going to do some thing where it uses a power rule on the left side, but what I would do is I just integrate linearly. I would just get y plus y cubed is equal to t squared over 2t squared. Oh, okay. Okay, cool. So yeah, we get y plus y cubed is equal to 2t squared plus c. Implicit solution. Okay. 18, 19, let's see this one. I don't know how many I can do before I freaking crap out, dude. Okay, so I think, oh, this one was cool. I tried this one at some point. Dude, have we done enough? You can only prepare so much. I just feel like there's so much material. Okay, that's going to be it. I think I streamed like 6 hours today. A lot of differential equations today.